Machine learning for MXene Informatics. This research is sponsored by the Circular Economy and Data Analytics Research for Sustainability, or CEDAR grant, to WPI from the National Science Foundation. The importance of predicting material properties. Being able to understand and accurately predict properties of a material would be a gigantic advancement for society. Information at the atomic level of a material can provide significant information about the properties of the material. MXene's background. MXenes are a family of two-dimensional materials, like graphene. In a two-dimensional flake of MXene, layers of early transition metals are interleaved with layers of carbon or nitrogen, and the general formula is given here. The T sub X in the formula represents the surface terminations, such as O, OH, F, and or Cl, which are bonded to the outer M layers. Brief project overview. There are 4 subgroups to this project. The first principles and machine learning teams will work together to select MXenes with desired properties. The Drexel lab group synthesizes these recommended MXenes and then sends samples to WPI's optical spectroscopy group to analyze the MXene sample to see if they match the predictions. UN Sustainable Development Goals. Predicting MXene properties more accurately, efficiently, and effectively will assist MXenes being used to their fullest potential. SDGs this project is associated with include affordable and clean energy with a large number of applications such as improving solar panel efficiency, battery efficiency, supercapacitors, electrodes for LIS batteries, and transport conductive electrodes and transport parent energy storage devices. Another goal is industry innovation and infrastructure. For example, electromagnetic interference shielding, chemistry and catalysis of MXenes, sensors and biomedical applications. And lastly, clean water and sanitation can be benefited by MXenes. MXene constituent elements. The M element in MXenes, which are transition metals, are listed in blue here. The X elements are carbon and nitrogen, and then the T elements are surface terminations. However, this is not a comprehensive list that you can see here. Possible constituent elements of MXenes. For sure, the list here, SC, TI, etc., have already been synthesized and should be used in predictions. It's also possible that later transition metals such as iron, cobalt, etc. could be used, but they have not yet been synthesized. Furthermore, it's been reported that lanthanides might be able to be used to produce MXenes. For surface terminations, there's a large list listed here, bromine 2, Cl2, etc. But this list can be significantly larger if using additional mixtures, especially mixtures including oxygen or halogens. MXene configurations to try. Here's a list of configurations. 2,1, for example, would be, an example would be titanium 2C. While an example of 2,2,3 would be Cr2, V2, N2, F2. It's possible to use more than just 2 transition metals in the same MXene. List of desired properties of MXenes. There are a number of properties that we are currently working on to predict, such as Fermi level, lattice constant band gap, work function, Bader charge, elastic moduli, magnetic, metallic, and density of states. There are some properties that will be attempted to be predicted by the end of the summer by our group, including electrical conductivity, carrier density, carrier mobility, carrier effective mass, thermal conductivity, Seebeck coefficient, optical absorption, and permittivity. However, there are some desired properties that might be too difficult to predict in the next few months, such as carrier lifetime sensitivity disorder, reflectivity, permeability, charge recombination, and THC range. Dataset description. 2 datasets were combined that were created using density functional theory to predict work functions. Here are preliminary results found from using Gaussian process regression. And the MXenes with the lowest work functions are to the right. Long-term project goals, it would be nice to predict MXenes with the lowest work function, for example, or other optimal properties. Short-term, there's likely not enough time to actually synthesize these materials. There have been many issues that have been faced such far, such as finding data. Future work will include the DFT group generating more data, creating models to predict semiconductor versus metal. And then far future work might include using transfer learning to use data for similar materials from MXene, predictions, using zero-shot learning to predict properties of MXene, etc. Thank you.